Hello folks, we're back with more multivariable calculus. Last time we were doing double integrals. We saw how to set these double integrals over general regions. Today we're going to discuss what happens when we set up the double integral, but the integral is too hard to calculate. Remember, that was a big issue when we were doing single variable calculus. Sometimes we could set up the integrals, but the integrals were hard to calculate, so we developed many methods, right? So we did stuff like substitution by parts, integration by substitution, integration by parts, integration by trigonometric substitution, integration by partial fractions, and many different methods. Now, the most useful of those methods for single variable calculus, the thing that took care of the most number of problems, was the simple integration by substitution. When you had single variable calculus, integration by substitution was very simple, and you could, by making the different substitutions, you could really solve very hard integrals. So that's going to be the idea today. When we're stuck with a double integral that's hard, we'll try to do substitution, but when you're in 2 dimensions, the substitution is not that easy. There is some work that needs to be done before you can go and actually make the substitution. So let's start by motivation so that this is not that dry. Let's say we want to find the volume of the region bounded above by the paraboloid z equals 16 minus x squared plus y squared, and below by the xy plane. Now, we already saw how we could draw these things. This is a paraboloid, so it's going to open up downwards, and it's going to intersect the xy plane on this circle of radius 4. How do we do that? Well, we can just realize that it's going to intersect the paraboloid is going to intersect the xy plane when z is equal to 0, so set the whole equation equal to 0, okay? Z was equal to 16 minus x squared plus y squared, so set it equal to 0, and of course you get x squared plus y squared equals 16, which is the circle centered at the origin with radius 4. So that pretty much tells us how we're going to set up our double integral. The region of integration is going to be bounded by the circle x squared plus y squared equals 16. So we're going to be interested in everything inside it. And we already saw that if we want to find the volume would be over the region f of xy over the region R, f of xy dy dx. Now, if you want to describe it as dx dy, fine. I'm just assuming it's dy dx here because it's going to be easier for this problem. Okay, so let's go ahead and do it. Now, in our case, this is not going to be very fun, right? Because if we draw the circle of radius 4, well, how do you describe the circle of radius 4? If we're doing vertical elements, if we're shading it like this, okay, going from left to right, if we're going like this, okay, and we're going to scan the area from left to right, okay, well, the top half, so the circle x squared plus y squared equals 16, well, throw it to the other side, we would get y squared equals 16 minus x squared. So you would get y is equal to plus or minus 16 minus x squared in the square root. So the plus side is the upper half circle, and the lower side is the lower half circle. We've seen stuff like this in Calc 1. Now, okay, so if I want to set the integral up, y is going to be between the upper half and the lower half. So y is going to be starting from the lower one, top minus bottom. The bottom is minus the square root. The top is plus the square root 16 minus x squared. And the y's are moving, the x values are moving. When we're scanning like this, the x values are changing from minus 4 to 4. And f of xy was equal to 16 minus x squared minus y squared. I distributed the minus sign, dy dx, okay? Now, to tell you the truth, this looks horrible, okay? Some of you might have realized that we can use symmetry here because this paraboloid is symmetric over the region. What we could have done is, instead of taking the whole circle, we can just take a quarter circle, the top quarter in the first quadrant, okay? Now, that would be just described by the upper circle, which is square root of 16 minus x squared. So now if I'm scanning this one, well, y goes from 0 to 16 minus x squared, and x goes from 0 to 4, there would be four of these quadrants to make the full circle, so I can multiply by 4. Okay, so this looks less scary, and I'm still going to have to integrate the same function. Now, okay, if you integrate it once, you'll see that it's not a problem. With integrating with respect to dy is not that big of an issue, but then you get all these square roots in your integral, and when you had square roots, it was kind of bad news, wasn't it? Because then we'd have to use trigonometric substitution. Okay, so that's something I really don't want to do right now, because these problems are just hard enough by themselves setting them up. So why do trigonometric substitution at the end? And what happens if we couldn't do trigonometric substitution, if I gave a different problem? And the idea is, well, let's try something else. Because the region is circular, the region R is circular, and the function, the paraboloid itself, is a very circularly symmetric thing, right? If we go back to the paraboloid itself, it's opening down like this, it's opening down like this, it's got a lot of circular symmetry. So I get this idea, hey, when we had circular symmetry, we tried polar coordinates in Calc 1, so why don't we try to do the same thing here? Why don't I try to do everything in terms of polar coordinates? So what I'll try to do is, since R is bounded by a circle, and the object we're dealing with, the function that we're dealing, the surface we're dealing with is very circular, it's a paraboloid, I'll try to use polar coordinates. Now remember the polar conversions? We had x is equal to r cosine theta, y is equal to r sine theta, okay? So if we do the math now, the region R, which was x squared plus y squared less than or equal to 16, the inside of the circle, can just be described, well, what is this? This is just the circle described as r equals 4, right? The outside is r equals 4. Or you can say x squared plus y squared is equal to r squared, and r is less than 16, so r is going to be between 0 and 4, okay, the positive radius. And what about theta? Well, we have to do 2 pi to go around the full circle, okay? So this integral that we had, this nasty integral that we had, minus square root to positive square root, minus 4 to 4, oh my goodness, the function, it makes you fall asleep already. Well, maybe I can write it using this, okay? Because it's the r is going to go from 0 to 4, okay? And theta, to go full around circle, we take 2 pi radius, it's going to go 0 to 2 pi. Now the function itself, what was the function? The function itself was 16 minus x squared minus y squared. Well, this is the same thing as 16 minus x squared plus y squared. And remember, x squared plus y squared was equal to r squared. So the function itself is pretty simple in polar coordinates as well. It's just 16 minus r squared. Then, of course, I'm going to integrate this with dr d theta. But what about the conversion? Remember, when you're doing substitution, there's always some term. When you're changing the variables, there's cos to it. How do I calculate, how I convert dx dy into dr d theta? Okay, so what is the conversion from dx dy to dr d theta? How would I actually calculate it? Okay, so we actually the region was easy. Okay, and the integral is going to be dr d theta. The function was easy. But what is this conversion? How am I going to calculate that? Okay, so that's what we're going to try to do today. What's going to go in here is the absolute value of what we call the Jacobian is going to go in there. And we're going to talk about a little about that. Okay, so let's generalize this. Okay, let's do this for general functions over general regions. Okay, and maybe the conversion you're doing is not polar. Okay. Well, how would this process work? I'm going to talk about this abstractly a little bit. Then I'm going to go into details so we see how to apply it. Okay? So the general question we're trying to tackle here is we are trying to find the volume of a surface described by, let's say, the function f of xy over a region R described in terms of x and y again. So we know that we're interested in these double integrals. The volume is usually calculated by, we can calculate it by We usually calculate it, we think about it in terms of x and y always. So we're going to do whatever this region R is, we're going to write down the function and then the dA. dA here is going to be dy dx or dx dy, depends on whether you did vertical elements or horizontal elements, okay? So the issue here is just like we saw a few minutes ago, the integral above, once we write down the integral, might actually be hard. It might even be much harder than the example we did. I'm going to show you an example that's horrible, to tell you the truth, but it's going to turn out to be very easy once we do the substitution. So we might therefore try integration by substitution just like we did in Calc 1. So let's say instead of describing the surface f of xy using x and y, we'd like to describe them using different variables u and v. In the previous example, we had the surface described, the paraboloid was described as z equals 16 minus the quantity x squared plus y squared. Well, if I described it then using polar coordinates in terms of r and theta, it was just 16 minus r squared. So maybe the integral, what's inside the integral sometimes becomes much simpler if you do the right substitution. That's the moral of the story, okay? So what does it mean that I'm describing this function in terms of u and v? Well, the derivative, then the independent variables x and y are going to be described in other independent variables called u and v, okay? So x is going to be a function of u and v, let's call it g, and y is going to be a function of u and v also again, let's call it h, okay? In the previous example, we had both x and y were described in terms of r and theta, okay? So what happens here is that this integral we have, r equals f of xy dA, okay? Well, we can describe it as, well, that's actually f of xy dx dy, okay? So now, if I can describe this region in terms of u and v, so it's not in terms of x and y anymore, in terms of u and v, I don't know how to do that yet. Okay, so I made a big question mark. Let's call this description of it as whatever the heck it is. Okay, and then substituting into x and y, we have f of g of uv and h of uv, and then the dA is going to be what? How do I describe dx dy in terms of du and dv? Okay, so there has to be some conversion that we need to do. Okay, so our problems are twofold. Okay, well, it's actually threefold. If we want to use u and v instead of x and y, we need to convert the region R to the region S. They're exactly the same region, okay? But R is described in terms of x and y, and S is described in terms of u and v, okay? Now R is going to be the xy, is going to be on the xy axis. S is going to be on the uv axis, okay? So they're going to look different. I'll show you what I mean in a few minutes. And two, once we do the transformation for the region, what we actually need to do is we actually need to calculate dx dy into du dv, okay? To do that, we will use something that's called the Jacobian, okay? The Jacobian. I really don't want to go into detail. The calculus books have some detail on it. It's kind of hard to talk about this Jacobian at this level. What you can imagine is we're trying to transform the dx dy are these tiny rectangles. Remember when we were setting up these double integrals, we divided the region, the rectangular region, into tiny rectangles, okay? So what we're doing them is we're changing them to these, instead of rectangles, we're trying to change them to u's and v's, okay? So the rectangles go to kind of like parallelograms. And we need to convert the area of the small rectangles into the area of these parallelograms. I mean, it's really hard to talk about it. So I'm not going to give you the proof of this, but the way you convert is you're going to convert your integral f of xy dx dy over the region R. The first thing you're going to do is you're going to describe this region as S, which is the description of the same region in terms of u and v. Then you're going to write your function in terms of u and v. And then you're going to multiply it by the absolute value of the Jacobian. Oh my goodness. And finally, the du dv. Okay? So this part, well, we expected to do this part and this part. So what's new? I know the formula looks horrible, but it's not that bad. Don't worry about it. What's the important is, what is this absolute value of j business going on? J for Jacobian, of course. Okay? So the way to do this is in 2 dimensions. You can do this in 3 dimensions also. If you want to calculate JUV, what you do is you take the partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, and partial of y with respect to v, and you take the determinant of that 2 by 2 matrix. Now, what's very, very important here is, this is where a lot of students make this mistake, is in the integral, we don't have the Jacobian. We have the absolute value of the Jacobian, okay? We have the absolute value of the Jacobian. So whatever you get here, you need to take the absolute value of it when you're plugging it into, when you're converting dx dy into du dv, okay? And here I'm going to talk about the reason of this. For those of you who've seen some linear algebra before, the issue here is, when you write f of x, y, well, you see the function in terms of x and y. I might see the function in terms of y and x, okay? So, I don't know, I'm having a bad hair day, or I'm having, I'm feeling very artistic today. You write f of x, y, you say the function of it is in terms of x and y, and I just want to argue with you. I say, no, it's in terms of y and x, okay? So, there might be actually a great reason why I might say that. We'll see later on. So the issue is, whatever we do it, okay, the conversion, it's still the same function. Whether you say it as f of xy or whether you say f of yx, it's still the same function. It's still the same surface. So the integral shall not change when you reverse the order of these variables, right? Okay. So when you reverse these, it shouldn't change. But if you reverse them, the determinant would be minus. Okay, the determinant would be minus. So that's why you might get the determinant positive, I might get the determinant negative, but actually the area conversion is always positive. Okay, so that's why we take the absolute value. So if I were you, I'd just memorize the formula. R is going to turn into S. Well, you got to do that. Okay. F, well, we're going to write F in terms of U and V. Okay. At the end, there is du dv. In the middle, all you have to memorize is that there is going to be the absolute value of the Jacobian. Okay. So let's actually go back to our original problem. Let's see how this is going to work out. This was a lot of theory. Okay. Let's see this in action. And let's see whether it's actually going to make things easier for us or not. So remember, we were trying to find the area bounded above by the paraboloid 16 minus x squared plus y squared, okay, and above the xy plane. Okay, so we already saw that the region of integration, when we're talking about the region of integration, was x squared plus y squared less than or equal to 16, or in other words, the inside of the circle centered at the origin with radius 4. Okay, so when we did vertical elements, we got this nasty integral minus 4 to 4. Okay, and y is going to change. The lower half is going to be y equals minus square root of 16 minus x squared. The upper half is going to be y equals square root of 16 minus x squared. The function f of xy dy dx, because I'm doing vertical elements. Okay, now the first thing we did, what I always suggest you do, is because this function is very symmetric, we can use symmetry. So I can just do this in the first quadrant and multiply it by 4, right? When you think about the paraboloid, it's symmetric. You can divide, if you divide into 4 equal pieces, right? You can just calculate the piece above this region and multiply it by 4 to get the total volume. So I said 4. Then how would I describe this region? Well, the top is going to be y equals square root of 16 minus x squared. Okay, y equals 16 minus x squared. The bottom is 0, so 0 to 16 minus x squared in the square root. And x is going to change between 0 and 4, and we want 4 of these babies. And that's, remember, where we got stuck. So now we were trying to use the polar substitution, x equals r cosine theta, y equals r sine theta. And in this case, we got that the region can be described as just, since it's the radius, it's the circle center that the origin with radius 4, that's just the area inside the circle r equals 4, or in other words, r is between 0 and 4. And it took us 2 pi radius to go around the whole thing, so we have 0 to 2 pi is theta, okay? And how did we convert f of xy? Remember, that came out to be 16 minus r squared. Now, all we have to do is we need to calculate the Jacobian r theta. How do we convert x and y's into r's and theta? And that's equal to x sub r, x sub theta, y sub r, y sub theta. We want to calculate the determinant of that. Now, x was, let's write it over here again, so it's right above. X is equal to r cosine theta, y equals r sine theta. Okay, so I'm doing partial derivatives. X sub r, the partial with respect to r, is just going to be cosine theta, right? I'm treating cosine theta as a constant. Now, if I do x sub theta, this time I'm going to treat r as a constant. Derivative of cosine theta is minus sine theta, so I have minus r sine theta. When I take the derivative of y with respect to r, I just get sine theta. And similarly, when I take the derivative of sine theta, I get cosine theta, so derivative of y with respect to theta is r cosine theta. If we calculate the determinant here, it's going to be cosine theta times r cosine theta, which is r cosine squared theta, minus a minus, right? Minus a minus, r sine squared theta. So since cosine squared plus sine squared equals 1, once we factor out r, we just get that this thing was r. Now, this is directly going to go into my Jacobian. This is the Jacobian. The absolute value is going to be the same thing. Reason here is, remember, the region described in terms of f of xy, in terms of xy, was the same thing as s described in terms of theta, r cosine theta. F of r cosine theta, r sine theta, absolute value of r, dr d theta. This is my r is equal to my Jacobian, right? Jacobian r theta. Okay. Now, it was really good news for us because, remember, for us, r was between 0 and 4. So r was already positive. And if I can do the same thing, I can do the polar integration in the first quadrant and just multiply by 4. So in the first quadrant, r would always be between 0 and 4. Okay. And theta would range from 0 to pi over 2. So we have r equals 0 to 4. Theta goes from 0 to pi over 2, and we want to multiply it by 4 at the end to find the volume under the whole paraboloid. Okay, the function we had already calculated was 16r squared, 16 minus r squared, so we get r dr d theta. Guys, memorize this because this is always the same when you do polar substitution. When you do polar substitution, instead of dx dy, you just slap on r equal r dr d theta, okay? And the order of integration is r first, d theta afterwards, okay? So it's always this, memorize that. So let's finish the problem up. It's getting boring. So we have 4 times 0 to pi over 2's, and r goes from 0 to 4. I multiply it through by r, and you're going to get 16r minus r cubed, dr d theta. If we integrate this with respect to r now, we're going to get 16r squared over 2. In other words, just 8r squared. R to the 4 over 4. And r is going to go from 0 to 4. And that's going to be inside the integral 0 to pi over 2 d theta. Plug in 4. We're going to get 128 minus 30. Plug in 0, you get 0. So it doesn't matter. Okay. So the integral now is 4 times 0 to pi over 228 minus 30 to the d theta. That's going to be 4 times 0 to pi over 96 d theta. So that's just going to be 4 times 96 theta, evaluate from 0 to pi over 2. And if you do the math, I think the answer comes out to be 192 pi. Okay. So that was that. Now, some of you guys might say, hey, rather than learning this Jacobian business, you just have to memorize r dr d theta for this example. I'd rather do this original problem, okay? I know my trigonometric substitution really well. hey, I'll just bear with it and I'll just do my trigonometric substitution. And well, that's not an option in general because of this very simple setup that we're going to do next. We'll see that in general we don't have that option. You just have to do substitution sometimes. Okay, so the question is, I'm just going to straightforward give you a double integral. We have some region and we're trying to integrate e to the y minus x over y plus x over this region. Okay, and so what is the region? We need to know the region. The region is bounded by the triangle with corners 0, 0, 2, 0, 0, 2. Okay, so I drew the region. This is 0, 0. This is 2, 0. This is 0, 2. So it's a triangle right like this. It's a right triangle like this. And we want to integrate this function e to the y minus x over e to the y plus x over this region. Okay, so I'm going to do vertical elements. We need to find the equation of this line. That's easy, right? That's just going to be y equals 2 minus x. Okay, so here is 0, here is 2, and y is going to change from 0 to 2 minus x. So y is going to go from y equals 0 to y equals 2 minus x, and we're going to scan this from left to right like this. X goes from 0 all the way to 2. And the function was e to the y minus x over e to the y plus x dy dx. Well, if you know how to integrate the first integral, this one, okay, let me know, all right, because I don't. Well, I know, but it will be really, really hard, right? It will be really, really hard trying to integrate this thing with respect to y. So that's a no-go, okay? We're not going to be able to do it like this. We have to try some substitution. So the thing that I try is, well, this y minus x, y plus x, it's really not making my life easy. I need two variables. I still need two variables. So I'm gonna make a guess here. I'm just gonna call y minus x u and y plus x v, so that this would be the integral of e to the u over v, which looks simpler. So let's calculate the Jacobian of that. Well, the Jacobian would be, the formula for the Jacobian is derivative of x with respect to u, derivative of x with respect to v, derivative of y with respect to u, and derivative of y with respect to v. Hey, hold on a second. I have u and v in terms of x and y. I don't have x in terms of u and v, and I don't have y in terms of u and v. To make things worse is, how would I describe this triangular region on the xy plane in terms of u and v? Okay, so Houston, we have a problem basically. We have an issue here. I will say, have no fear. Your friendly neighborhood mathematician is here. If we do this slowly but surely, we'll get to someplace. So first, we don't like this. Our idea was not to write u in terms of x and y and v in terms of x and y. Just the opposite. We want to write x in terms of u and v and y in terms of u and v. So for this example, that's relatively simple, right? We can actually find these. When we had u equals y minus x and v equals y plus x. So notice that if I add them up, the x's will cancel and u plus v will equal to 2y. So from there, I can just solve for y. Y is equal to u plus v over 2. That's great now because y is in terms of u and v. Similarly, if I subtract v from u minus v, well, the y's will cancel out and I'll get minus 2x. So x is the same thing as v minus u over 2. Okay? So now this is going to now I can calculate my partials. Derivative of x with respect to u is minus 1/2. Derivative of x with respect to v is 1/2. Derivative of y with respect to u is 1/2. Derivative y with respect to v is again 1/2. So we have this 2 by 2 matrix. Very simple 2 by 2 matrix. So minus 1/4, minus a 1/4. So that's a minus a half basically. Now the next order of business is we have to convert the region, this triangular region, in terms of x and y to a region in terms of u and v. So what I did was very simple. Basically, we have this rectangular region, right? Well, with triangular region in the xy plane. So I calculated what would happen to these 3 points when we plug them in here. Okay, so the point 0, 0, when you plug it into here, you get u is supposed to be equal to 0 and v is supposed to be equal to 0 then. So the point 0, 0 goes to where? In terms of u and v, it still goes to 0, 0. So it's basically stayed where it was. Okay. Now let's go back to the point, let's say 0, 2. When you plug in 0, 2, it's going to be 2 minus 0, so u is going to be equal to 2, and v is going to be equal to 2. So 0, 2 goes to 2, 2, and you'll see that 2, 0 goes to minus 2, 2. So this triangular region in the xy plane went to a triangular region in the uv plane, but it was a different triangular region. It's this triangular region. The vertices 0, 0 went to 0, 0, okay? 0, 2 went to 2, 2, and 2, 0 went to minus 2, 2. Okay, so we have this triangular region. Okay, well, it's still triangular. It's not too bad. So it's the UV plane. So let's get the formula of this. This would be the V equals U line, and this would be the line V equals minus U. Okay, so what I'll do is I'm gonna now scan this using horizontal elements. If you want to do vertical elements, the issue is you'll have to separate the integral up, right? You'll have to if you did vertical elements, you'll have to go from minus 2 to 0 and then 0 to 2 because the functions change. Here you're going down to v equals minus u. Here you're going down to v equals u, and the function e to the u over v is not symmetric, so you can't do that trick of multiplying by 2. That will be very dangerous. So instead, we're gonna do this. So I'm gonna write everything in terms of u is equal to v, and u is equal to minus v. Okay, so all right, let's do this integral. So the original integral was y equals 0 to y equals 2 minus x. This horrible thing, x equals 0 to x equals 2 dy dx. What did that turn into? Right minus left, u is equal to v, u is equal to minus v, and we're gonna go, the elements go from minus 2, sorry, not minus 2, my bad. Yeah, we're doing horizontal elements. So v itself goes from 0 to 2. So u goes from minus v to v, and v goes from 0 to 2. And the integral is now very simple. E to the u over v. And I have to remember, we have to take the absolute value of the Jacobian. What was the Jacobian? Minus 1/2. So I'm not going to write minus 1/2. I'm going to write 1/2. Okay, absolute value of minus 1/2, which is 1/2, du dv. Okay, so now I pulled the 1/2 out, and if we integrate this, e to the uv with respect to u, that's like doing e to the x with respect to x. Hey, the integral of e to the u over v is just going to be e to the u over v, but because we're dividing by v, we have to multiply it by v. Think about trying to integrate e to the x over 2. What was the integral of that? It would be e to the x over 2, but because you're dividing, you'd get to 2, so that would be 2 times e to the x over 2. Okay, same thing. V behaves like a constant, so because it was dividing, I have to multiply. Okay, and this is going to go from u equals minus v to v. The outside integral is still dv. So wherever I see u, I'm going to plug in v. So when I plug it in, I'm going to get v times e to the v over v, which is just e to the 1. Okay. And when I plug in minus v, I'm going to get minus v over v. So that's going to be e to the minus 1. So we get v times e minus v times e to the minus 1 dv. Let's make this simpler. Let's pull out v. And we get v times e minus 1 over e dv. This is with respect to v, so that's going to be just v squared over 2. We still have the half, v squared over 2, e to the e minus 1 over e, evaluate from 0 to 2. What happens on the bottom? You have a 4. When you plug in 2, v squared is going to be 4, so they cancel each other out. When you plug in 0, you get 0. So the answer is e minus 1 over e, and that's it. Okay? So the moral of the story is this original integral would be really, really hard to calculate, okay? Really, really hard to calculate. By making the substitution, by just calling this u and calling this guy v, and then just calculating the region in terms of u and v, and then calculating the Jacobian, converting dx dy into u and v, we got a much simpler integral, much simpler integral to deal with, and then we could calculate it. I'll tell you a story here. When I was a grad student at UIUC, I was TA for multivariable calculus, and we had these double integrals, a bunch of homework questions the kids were supposed to do. These double integrals, they were lengthy, so they set them up, they did them, and whatnot. So each of the kids handed in basically a stack of paper, and I had to read all those homeworks. Most of the time, the kids were good. They got the answer correct. Then I got this kid that just had 1 or 2 papers. The whole homework was just 1 or 2 papers. So I thought, no way, no way this kid did this homework. It couldn't be so short. Then I started reading the homework, and he did these crazy substitutions, and he would simplify the integrals down. Suddenly the integral will simplify down, it'd be a one-line integral, okay? So if you know what you're doing, and you make the correct substitution, you can simplify tough integrals into really, really simple integrals. Well, you might ask, well, how do I get to the point where I know what I'm doing? How do I get to the point where I know what to substitute? For this example, it was kind of easy. We just guessed u and v. So sometimes it's kind of obvious. Sometimes it's not that obvious. The way you learn this is just basically the way you learn integration is you do lots of examples, okay? So by doing lots of examples, you learn more substitutions, and stuff becomes easy. So I'm gonna call it a day here. That was multivariable substitution for us. Next time we're gonna see more substitution, but we're gonna see how to do more substitution in more dimensions. Okay, so what happens when we have functions of 3 variables? Okay, what happens when we have triple integrals? We haven't done triple integrals yet. We're gonna do that first, and then we're gonna do cylindrical substitution, spherical substitution, and basically different substitutions. So this Jacobian is gonna come up again. Now, if you are doing this with multivariables, if you have both x, y, and z, not a function of x, y, z, say that's described as in terms of u, v, and w, instead of a 2x2 matrix, you're going to have a 3x3 matrix. Don't worry about it. We're going to see it next time. So I'm going to call it a day. Take care. Bye-bye.